You know, there are sine waves all around us. Everywhere you look, if you look for them, you can see sinusoidal motion. Pictures of sinusoids at the beach, when the flag is waving. You can see sine waves in something as simple as a clothesline, if someone pulls on it and lets it go. You could even, when you have nothing better to do, and you're hanging out somewhere, and you don't really, and you're probably bored to tears, you can think about or look around you and say, do I see any sinusoidal motion? Okay, so sometimes it's hard to recognize. Like here. This is a pendulum. It's made with plumb bob. I used to be a surveyor, so I'm familiar with plumb bobs. And when you put them on the end of a string, they do very interesting things. So we'll get this one swinging. And please don't get hypnotized here, because I'm not sure I know how to read it up. So as this goes back and forth, we can make some observations. Now, the actual period of the pendulum, and you should know what that means now because we've been talking about sinusoids, it's the time it takes for the plumb bob to complete the cycle. So now if I told you that, and so normally you would look at this and say, okay, so it's like a swinging pendulum, big deal. Well, it's actually a sinusoidal motion. If we took the horizontal displacement as a function of time, we would see that it's, first of all, it's periodic. Secondly, it goes first positive and then negative. And it goes through zero, which is when it's hanging down. So it turns out it really is a sinusoid. But there's something more mysterious and subtle about this motion. And that is, if you're looking at the sinusoid of displacement, you can more or less see that this is a peak, a positive peak, this is a negative peak, and in between it goes through zero. A full cycle takes some amount of time. The way we do this in physics class is we measure 10 swings, and then that time, and then we divide by 10, and that gives us a more accurate measure of the actual period, the time it takes to go from one side to the other. This looks like maybe a couple of seconds. It depends on the length. The longer the length, the slower the plumb bob. And a really cool demonstration of that is, let's get it going pretty good, which is hard to do when you're holding it. And I'm going to try to grab it right here and then pull it up. And you can see that the period, the time it takes to go through a cycle, is greatly reduced. There's a formula for that, and you can look it up on the internet. But this is not a course in pendulum, it's a course in sinusoids. So what else do we have to say about it? I said there was something mysterious. What's mysterious is when the pendulum is here, its velocity, its motion, is instantaneously zero. It's stopped. And when it's down here, when it's on this left-hand side, it's also stopped. And when is the pendulum moving? Or at what position is the pendulum moving fastest? When it's vertical. And it turns out the plot of the velocity of the sinusoid, or of the pendulum, is also sinusoidal. And that's why sinusoidal motion shows up everywhere. Because the curve of the displacement and the curve of the velocity, or the rate of change of the displacement, both sinusoids, both have the same frequency.